Hello everyone, welcome back to Geospatial Tube. Today I'm gonna show you how to generate drainage density mapping from digital elevation model with the help of ArcGIS Pro to generate landslide susceptibility mapping. In the previous video, I have shown you how to generate different parameters that is related to a factor for landslide susceptibility mapping like elevation, slope, aspect, curvature, and LS factor. Today is a turn for the density mapping. Before we go to the practical aspect, I would like to remind you to subscribe my channel and hit the bell to gain some kinds of update from the channel. Let's get started. First of all, let me give you a brief explanation about the general steps that we follow to generate drainage density mapping. At least we follow 6 steps. The first step is we need to fill the digital elevation model to avoid errors. The second step is we are expected to generate a flow direction based on the direction movement of the topographic structure of an area. Since we generate the flow direction, the flow accumulation is generated on the basis of flow direction, and finally we decide our threshold to separate which area have more flow accumulation and which one is insignificant in nature. And the fifth step is we need to convert raster data to polyline because to compute a drainage density mapping, we need to know the length of each stream from that of our study area. Finally, we compute drainage density mapping using line density with the help of ArcGIS Pro. The general formula is that drainage density is a byproduct of total length of stream within a catchment over a total area, and total length of stream is measured in terms of kilometer, whereas total area is measured in kilometer square. So drainage density is a function of total length of the stream over total area of the catchment or study area. Let's get started. So, as I have mentioned earlier, the working data is a digital elevation model which ranges between 952 up to 2,897 meters above sea level. The red color indicates the place with higher elevation, whereas the green one indicates relatively flat or lowland areas. So, I have filled the digital elevation model in a previous video. Then I am not in mandate to fill the digital elevation model. So step 1 is filled already in the previous video. Now I will generate the flow direction on the basis of the topographic structure. Here there is a highland area, and it is the flow direction can be in different directions. So to compute the flow direction of this topographic structure, let's go to analysis, or you can go to view. This is an alternative. Then click geoprocessing. The geoprocessing wizard is available in the right side of our computer. Then click toolboxes. There are different available toolboxes to compute different parameters, and the main intention is to compute a flow direction of a steady area. To perform that, select spatial analysis and scroll down. Here there is a spatial analysis tool. From spatial analysis tool, we need to select or find hydrology. From hydrology, there is a flow direction. Double click the flow direction. The input parameter is a digital elevation model that we have prepared based on our study area. So the input surface raster is a field name of this study area. The output flow direction raster should be saved in your working directory. So you need to set your working directory first and give your own name. I will give a default flow direction as a name of my output file. D8 is a deterministic aid method. There are different methods to compute a flow direction of certain topographic features. So D8 is my method. Heat run. Automatically, I gain the flow direction raster from the digital deviation model of my steady area. This is a raster dataset that indicates from 1 to 128. If you are interested to know the meaning of 1 to 128, you can refer back to the previous videos. So this is the different flow direction of my steady area. There are compass point and cardinal as well as subsidiary points within our compass point. The third step that we compute is flow accumulation on the basis of flow direction. Then let's get back to geoprocessing, and here there is a flow accumulation. Flow accumulation is related to the computational of cells. So the input data is a flow direction that we have generated earlier, and the output accumulation raster, you can give your own name, and I will leave by default flow accumulation. And the method is deterministic gate method, heat run, and automatically we obtain the flow accumulation raster data set from a flow direction data set. This is the raster dataset. The flow accumulation of this raster indicates that 0 indicates the higher elevation because water flow from highland to lowland, and accumulation is expected to lower areas. Then the deep black color indicates the highland area, whereas this number indicates that there is high amount of accumulation. Accumulation indicates that water accumulation as well as sediment. So this is a flow accumulation. From this flow accumulation, we generate the fourth step. We need to have a threshold to perform that. Let's get back again to geoprocessing tool, and we need to select the map algebra. From map algebra, there is raster calculator. Double click on raster calculator and use a flow accumulation. Double click flow accumulation. The threshold is greater than 1000. So you are expected as usual to set your working directory and give a name for your output, and this is the flow accumulation raster and heat run. Automatically it converts on the basis of threshold above and below the threshold of 1000. On the basis of our threshold, 1 is the area which contains above 1000 and 0 is below 1000. So this map indicates that there are streamlines, and to compute the drainage density, each stream have its own lengths, and we sum up the total length of all the streams which is available on the map and divided by the total area of our steady area to gain a drainage density map. But the next step to compute a drainage density map is we need to convert this raster dataset to a vector. To perform that, let's get back to geoprocessing tool, and let me collapse spatial analysis tool because I need to convert this raster data to a vector dataset. So select conversion. Here is conversion, and I do have the raster dataset, and I need to convert this raster dataset to vector. So select from raster to polyline, because there are different linear structures in this dataset, and I need to convert to a polyline instead of polygon. So the input raster dataset is the flow accumulation raster that is generated by using a threshold with the help of raster calculator. The field is value, and here there is raster to flow accumulation. You can rename it as from raster to vector, raster to vector. You can rename it in your working directory, then run. here is the product. Let's collapse and uncheck all the other data set to visualize. Let us convert the linear feature. Since it is a river feature, I would like to convert this. I go to property. Let me show you. You can double click here. Let me show you. You can double click this feature and you can convert this color by go to properties. So since the linear feature is representing that of a river, I would like to take this color. So this is all the linear feature you can compute by opening the attribute table to calculate the total length of each stream. To perform that, you can right click here, then open the attribute table. Open attribute table. You can add field. To add field, click here, add field. Automatically it redirect to the other tab. Let me provide a field name as length. Length is always measured in terms of numeric value, so the data type should be double because I need to have a decimal degree. And since the number format is numeric, I would like to select number. Click here and the category should be numeric, then hit OK. Go up and save the field that we have generated earlier. Close this tab and get back to the main one. This is the length. To compute or to calculate the length of each string here, right click here and calculate geometry. The input dataset is raster to vector, and the field is the length that I have added, and the coordinate reference system is the current map, and length is always measured in terms of meter, so the length unit should be kilometer. Then finally hit OK. Automatically generate the length of each stream which is available here. So to know the total length of each stream, you can use statistics or you can use a summary. Let's take statistics. From statistics, there are different values. There is mean, median, standard deviation, row, and the like. So the total number of, then automatically the data distribution is indicated here. You can also have a look. The total, the minimum is 0.02, the maximum area, the maximum length of stream is 3.13, and the total sum of this stream length is about 162.5, approximately 162.5 kilometer. Let's get back to our notepad because I have got the total length of stream. The total length of stream is this much over, we will calculate the total area of our study area. So let's get back. You can remove this and back to the main concern. Final step is we need to compute the drainage density mapping using line density. To perform that, let's get back to your processing tool and let's select the tool that helps us to compute the drainage density. Let me collapse this conversion tool and scroll down to spatial analysis tool. From spatial analysis, there is density. There are kernel density, line density, point density. Since my data set is linear feature, I would like to use line density. Double click. Input polyline feature is a vector, raster to vector. And I would like to set my spatial resolution as 20 meter. It depends on your preference, since my objective is designed to compute the landslide susceptibility mapping for this steady area within 20 meter spatial resolution. I use 20. So the final map is a drainage density map. So let me give a name DD. DD indicates a drainage density. The total area is square kilometers because the area is measured within kilometer square. Other most important thing that we should consider here is that to generate well-organized drainage density map of our steady area, we are expected to set our working environment, go to environment. So the output coordinate system is the current map. Automatically, it will generate the map projection that we have used within this system. The processing extent should be set. The processing extent is the steady area, the Warada boundary of this black color. So it is automatically generating the extent of the shapefile. And the mask is, we can easily mask on the basis of the Warada boundary as well. Then hit run. Finally, we come up with a drainage density map of our steady area. So this is the drainage density map of my steady area, and we can have a look with better visualization by converting the color scheme. Double click here, or right click and go to symbology. From symbology, you can have a look with your color preference. Let me select this, and the number of class should be 5. So this is a final drainage density map of my steady area, but on the basis of my threshold to compute landslide susceptibility mapping, we need to reclassify our dataset on the basis of our data, on the basis of our threshold. So let's get back to the drainage density. This is, as I have mentioned you earlier, a place with 0 to 0.5 kilometer per kilometer square is a drainage density. Kilometer indicates that the total length of a stream on kilometer square is a unit for total catchment area. So if a number lay between 0 to 0.5, it is very low susceptible for landslide because the drainage density is very low. So drainage density have its own relation with landslide susceptibility. If the value is greater than 2 km per kilometer square, this area is highly susceptible for landslide. So on the basis of this, I would like to reclassify our raster data into 5. Let's get back to the ArcGIS Pro environment. So to reclassify, what we are going to do is let's get back to geoprocessing tool and scroll down to reclass. Here there is reclass. Double click here and click reclassify toolset. From this tool, there are the input raster data is the drainage density map that we have generated, and we should reclassify or classify into 5. So the minimum is 0.5. You can refer the Excel data sheet. So 0.5, 1, 1.5, 2, and greater than 2. Then the first value should be 0.5. The second one is 1, the third one is 1.5, 1.5, then 2, and above 2. So the value indicators here is that 0 to 0.5 is 1. 1 means very low, susceptible for landslide. From 0.5 to 1 is 2, low. 1 to 1.5 is 3, moderate, susceptible for landslide. From 1.5 to 2 is highly susceptible, and from 2 and above is very high susceptible for landslide. So this is a reclassified drainage density. You can save in your working directly by providing your file name. Run. Let's get back with a final drainage density reclassified map, and I will set the symbology for better visualization. Right click here, go to symbology, and let me select color. Let me select this, and this is the final drainage density map. The red one indicates that the area on the basis of drainage density, the area are highly susceptible for landslide, whereas the green is low susceptible for landslide. This is all about today's video. If you have any question related to drainage density, please don't hesitate to ask. Thank you very much. Have a good day.